In today's lesson, we're going to take a look at how you assemble your components in Fusion 360 by creating joints versus mates, as well as the different joint types, the capture position command, as-built joints versus ground command, and motion studies. If coming from SOLIDWORKS or similar CAD software, then you'll most likely be accustomed to adding several mates to fully constrain and create just one effective joint. Fusion 360 does things a little bit differently by adding a joint and limiting all degrees of freedom, then simply selecting the respective kinematic joint to free up the required motion. Let's go through the 7 types of joints available, and I'll show you a few simple examples in use. First, the rigid joint locks two components together, limiting all degrees of freedom, i.e. no movement between either component. Revolute uses a rotational motion around one joint origin. Slider joint allows you to make a translational movement along a specified single axis. Cylindrical is a combination of revolute and slider, where you have one translational and one rotational movement along the same axis. Pin slot is similar to cylindrical, although the rotational movement is not constrained to the same translational axis. Planar utilises two translational and one rotational movement on a single axis. Finally, you have a ball joint which gives you full rotational movement in all three axes. For each joint, you can also amend the respective planar or revolute axes maximum and minimum values to align with your assembly, giving you complete control over your joints and their motion. Here I am amending the maximum and minimum revolute and slider joint limits to show you how the joint's movement is different when compared to the previous one. Before I show you these joints in action, I would like to explain the capture position command and as-built joints versus grounding. The capture position command, as the name implies, captures the repositioning of a component in time after moving it in any axis, which can be particularly useful to quickly evaluate and remedy interferences for position-dependent assemblies. The command is captured in the timeline and is treated like other commands where it can be edited or suppressed, for example, meaning any capture positions are not permanent and can be easily reverted. In this example, I need to create some cutouts on our Geneva wheel to allow the drive wheel pin to slide in and out. I already have some joints in place, so I'll rotate this wheel to get into position. Two ways to do this are to rotate the wheel manually, then select capture position in the toolbar. I'll revert this so the move is not captured and show you a more accurate way. First, bring up the move command by pressing M or from the toolbar. Make sure components is selected and select the drive wheel. Rotate by 90 degrees, select capture position and hit OK. Now the pin is in the correct position and I can see this command captured in the timeline. As I mentioned, you can always quickly revert this position back to the original by suppressing the command or moving back the timeline. I can now create the cutout based on this position and pattern this feature before finishing the assembly. Capture position should be treated the same way as any other feature, such as extrude or pattern, in that it appears in your timeline and can be edited at any time. Now I'd like to take this moment to explain the difference between the ground command and as-built joints when working with sub-assemblies. In SOLIDWORKS, you will typically find yourself fixing a component, then building the remaining components around it. Fusion 360 is slightly different, although achieves the same result. Here I have created two sub-assemblies using the same design, although with some subtle differences. In the first, you can see the base plate has been grounded, which means the component's origin is locked to the origin of the top level design. I cannot move this base plate, yet I can move the mechanism using contact sets and joints. The second example, instead, uses an as-built rigid joint, which locks the geometry of a component to another component or, as in this case, the top-level design origin. Again, I cannot move the base plate, yet the mechanism still functions. The main difference lies when I want to bring these sub-assemblies into a much larger assembly. Here I have inserted a copy of each into a new assembly and will create an as-built rigid joint by pressing Shift J for each of the top level design. With our as-built joint assembly, you can see I am still unable to move the base plate, and again, with the contact sets in place, the mechanism still functions as intended. However, for the grounded assembly, when I repeat the action, you can see everything is free to move in space, and I am unable to rotate the mechanism. The reason being is the ground command references the sub-assembly top level design origin, which is now changed, meaning this reference is lost when inserted into this assembly, and you can see that there is now no red pin next to the base plate. With the as-built joint example, the geometry is referenced, which has not changed, meaning we still have our references maintained. The ground command can be useful if you need to quickly test a feature or save on some computer resources when working with multiple joints, although as a best practice, you should use the as-built joint, particularly with sub-assemblies. Now heading back to our engine, I'll make sure to use an as-built joint between our engine casing and master assembly before adding the respective kinematic joints I mentioned earlier. I know that the piston only needs to move in one translational movement along a single axis in the engine block, so I need to select the respective joint origins that appear on the component, then I'll use a slider joint to replicate that joint. Now I'll add a revolute joint between the crankshaft and the engine block, giving us one rotational movement. I'll also use this same joint for the connecting rod and connecting rod journal. One quick tip here is to hold Control or Command on a Mac to lock in respective joint origins to a face or feature you're hovered over. This makes it easier to select those that are difficult to reach or out of view. Finally, I want the piston pin to always be central to the piston. In this case, I can use a Between Two Faces command found by right-clicking and selecting the respective faces. Again, I can use the Control or Command button on a Mac to constrain to a respective face or feature before I set this joint to rigid. In other CAD software, you may have found yourself creating planes to generate the same feature, yet in Fusion you can achieve this in a few clicks. Now when I go to animate our model, you can see the joints working together. As Fusion 360 opts for a top-down modelling approach, you will find components that are modelled based on existing component geometry. As such, the component is designed in place, which is where the as-built joint comes into play. You select the components rather than the geometry origins and define the joint type, giving you a quick way to add respective component-based design joints. I have one final model prepared to show you a few more features with joints. I mentioned briefly that you can define the joint's limits for each movement by right-clicking on the joint and selecting Edit Joint Limits. This is similar to when you set the start, minimum and maximum values in SOLIDWORKS, and by dragging the component you can see the defined joint limits in action. Alternatively, to get more accurate results, you can utilise contact sets to establish joint limits by moving a selected component until it collides with another selected component. First enable contact sets in the drop-down menu, right-click and select New Contact Set. Then select the two grippers on the robot arm. Press OK, now drag one of the grippers towards the other gripper and you will see it stop when it comes in contact, meaning the absolute limit has been reached before an interference occurs. Then, by double-clicking on the joint glyph, we have our value and can assign this to our respective joint limit using the same Edit Joint Limit command. You can then suppress the contact sets, drag the gripper, and you'll see it stop at the point of contact. And finally, a motion study lets you analyse the movement and rotation between joints, which helps you understand how your product and its components will interact with each other in real life. To create a study, first select Motion Study from the drop-down menu or shortcut key, which will open the dialog box. Click on your selected joint, making sure the visibility is on in the browser tree, and in the dialog box you'll see you can set the time or step at which a rotation or movement occurs for the respective joint's degree of freedom and to what value. We can also select the mode, whether it's one direction, bidirectional or repeated, as well as the speed, to fully understand how the components move in relation to each other. Repeat this process for any other remaining joints and you now have your finished motion study. That's all for this lesson on joints versus mates, and I'll see you in the next one.